So today we are going to learn about the administration of Cassandra clusters, basically monitoring, managing, and doing some performance tuning, etc. How do you really want to manage a Cassandra cluster? Okay, it's basically Cassandra administration. So agenda basically would be, how do you actually plan Cassandra cluster deployment? So basically you have to do some planning, right? So when you say capacity planning, etc. If I have to pick up a choice as to what is the number of nodes that I should be using for forming a cluster. So some of those choices you have to make. So for that one, how do you actually make the decisions? How do you actually go and do that capacity plan? That's something which we look at, and then we look at some of the basic configuration of Cassandra. How do you monitor a Cassandra cluster? How do you maintain a Cassandra cluster? How do you add a new node or remove an existing node? How do you do load balancing? There are many different things that can be done. And then on a security lines, how do you really give different permissions for the schemas to the users? And then other thing is, how do you tune the performance? Okay. Okay, so let's go forward. We touched upon 4. So cluster deployment. So when you plan a deployment, you surely need to see, you need to understand what is your capacity that you're looking at. See, what is the amount of application data that you want to support, what kind of hardware you want to use, so the various different things, like what is the number of nodes that you need actually for your cluster. That's your capacity planning. The type of hardware that you use, the key space replication options that you will really have, and then the node configuration tools. So we'll talk about each of them in detail as to what they actually mean and the purpose behind them. Okay, coming to hardware selection. So what are the various parameters that you would look for when it comes to hardware selections? You surely have to select the CPU, the speed of the CPU that you really want to use. What is the amount of memory that you would actually use, or RAM basically, the DRAMs that you would need for a system to deploy a cluster. Then what is the type of network that you would use to connect, the type of connections between the nodes in the cluster itself, and then what is the disk space, how much disk space you would actually need for say storing say 100 bytes of 100 kilobytes of application data. So how do you actually plan your disk sizes? So those are some things which we will learn in detail. Okay, so as we all know, right, memory is more memory naturally means larger cache size, which automatically means fewer SS tables, because you end up having bigger mem tables, which means that I can have a lot more data inside the memory, and I do not have to write it or serialize it to a disk-based representation, which is SS tables and etc. So hold more recently written data always. So more memory automatically means larger mem tables, fewer SS tables, and larger cache sizes, which surely is a good advantage. So it depends on how do you want to deploy it. So how much memory is that you have at your disposal. So if you look at it in general, it's a good refinement with the overall performance. So if you have more memory, please go ahead and add more memory. It's as simple as that. So coming to disk, a very important part of the entire setup. How do you do a disk selection? So there is something called capacity and IO throughput. So the two different important factors that you would look for when it comes to disk selection. Okay, let's talk about disk in detail anyways. So coming to CPU, we always talked about CPU, a general thing, right? We already talked about currently general mechanism is typical deployments of Cassandra clusters actually works with 8 CPU cores, because that sort of gives you a best price performance ratio in a Cassandra cluster. So the most commonly used versions are the 8 core systems. So one thing is, we all know, right? So it's very highly concurrent and naturally will benefit from many CPU cores. But if you look at increasing or rather scaling vertically, where you're adding more and more CPU cores in the system, the price automatically goes up of your hardware systems, right? So if you want to get a best price performance ratio, the recommended configuration for a Cassandra cluster is 8 CPU cores, or rather the most commonly used version is 8 CPUs. Virtualized machines, yeah, there are many mechanisms what you can actually do using VMs, and because almost all the cloud providers actually follow that model. A network coming to be, it has to be mainly reliable and absolutely redundant network interfaces, because you don't want the communication between the nodes go down, which automatically creates a problem, and which we all know. We have seen how the amount of communication that happens between the nodes inside the Cassandra cluster, because gossip sort of runs every second, and so hence it has to be absolutely reliable and redundant as far as the network interfaces are concerned. It should handle traffic without any bottlenecks. So now disk capacity planning. What is the disk capacity planning? So disk capacity planning, when you look at it, I think the two important factors that we need to talk about is the user data size, so basically the application data, and the usable disk capacity. So basically, if I pick up a disk of say 1 TB or 1 terabyte, how much of it is actually can be used for application data, or basically how much is the usable disk capacity, and how much is basically for the internal overheads of multiple copies, the in-memory stuff getting written into the disk-based systems. So you have mem tables which are already there, and they get written to SS tables, and SS tables have to be combined and put it back for compaction while doing the compaction, create new SS tables. So there's a lot of activity that happens internal to the Cassandra node. So as a result, the amount of disk capacity that is usable, or rather usable for application purposes, will be much less than what is the actual disk capacity. So let's understand how do you calculate that part of it. Okay. So usable disk space per node into number of nodes is basically the usable disk space, right? It's per node into number of nodes gives you the total usable disk space in your cluster. So assuming that you have something called raw capacity, which means like you have, say, you picked up 1 TB disks, so into the number of disks. So for example, you have 5 disks, so your total capacity, raw capacity, is about 5 TB. Now there is a basic formatting overhead, which is about 10%. So reducing the formatting overhead by 10%, you will basically have 90% of the formatted disk space. Now formatted disk space actually has to be multiplied by 50%. The compaction and repair disk discount, which has overhead of about 50%, which means that your total usable disk space is exactly half of your formatted disk space. Now assuming that you have started with 1 TB as the raw capacity, so because of the 10% gone, you're talking about almost like 900 GB of the disk, which is in the formatted disk space level. Now out of 900 GB, we are talking about only 50% being actually usable disk space for the application, which means that if you have a 1 TB disk, then application can be, you plan only 450 GB for the application. The rest of the disks is actually you've used mostly for the overhead as well as all the compaction and repairs that could happen inside the system, and etc. So you should always plan for 45% of your disk space, actual raw disk space, as your application. So in case if you have if you want to support, say for example 10 TB of application data, what you're talking about is basically almost like close to 20 nodes with 1 TB disks, right? So because just about 450 GB is what you can use per node, so we are talking about close to say 20 or 25 kind of nodes with 1 TB disks would be needed to actually support 10 GB of application data. So yeah, so indirectly saying that 45% of the actual raw capacity is what is usable for the application, and the rest of the things should be left for system to work with. Okay, so coming to the node config options, what are the various different types of node configuration that you can do inside the Cassandra.YAML? The settings that you can do inside a node configuration can be broken down into 4 different parts. One we call it as gossip settings, storage settings, partitioner settings, and snitch settings. We already looked at some of it basically, but we will probably spend some more time just to understand the things in more detail. First is storage settings. We already looked at it. What is the commit log directory and the data file directories. So the default one is varlib Cassandra, so that needs to change in case if you want to really go and write it to a different particular folders, because it actually has a default folder of varlib Cassandra. But in case if you have any, because varlib Cassandra is owned by root, you want to change it, you can change the commit log directories, the data file directories, and then the saved caches directories. Those three things for you to actually control the storage of your node, Cassandra node. Okay, that is the storage settings part of it. Now when it comes to gossip settings, gossip we all know, right? It's basically talking about one is the listen address, the IP address of the particular node which the other Cassandra nodes will use to connect and communicate. So one is naturally the listen address, the other one is the cluster name. It's actually the cluster is name is basically signifies the bigger entity into which this node is part of. So it's a mechanism of grouping a set of nodes into one single cluster. So the cluster name, actually all nodes which belong to one single cluster, they all have the same cluster name. Similarly, there is something called initial token. Now this has actually gone away and said they use something called virtualized nodes, that we will talk about it. But so the initial token basically says what is the responsibility of this particular node, what is the hash that it is responsible for, which tells basically the partition, the particular data partition that this particular node is responsible for is actually indicated by the initial token parameter inside the configuration. Then the storage port, basically the internode communication port, it's something which is default is 7000, should be same for every node in the cluster, absolutely same to everyone, because everybody talk to each other, and so they need to have one common mechanism, one common port which they will use to connect to each other and talk. Coming to seeds we already understood what seeds are. Seeds basically is a list of all comma delimited list of node IPs, which basically help in the bootstrapping process. So in case if a particular new node is brought into the cluster, or and it needs to obtain the metadata, so that it looks at this list of seeds and then picks up one of the node from that seed list and connects to him and obtains all the metadata. And the list of seeds should be exactly the same in all the nodes. Every node inside the cluster have to have the same list of seeds. Okay, and it should always be including a node from each data center, absolutely, because in case if a particular say if you have multi-data center deployment, and in case a particular node goes, you're adding nodes in different data centers, then it would rather go to a seed which is local to the data center than actually go to a seed which is remote to the data center, which is in a remote data center. So that's the reason why you should have in the seed list one node from each data center at least. Okay, this is gossip settings. Partitioners, there are two types of partitioners. One is called the random, the other one is the byte order. So what does a partitioner do? It basically determines how the data is distributed across the nodes. The random partitioner basically makes sure that it's absolutely consistently distributed across the load is distributed across the nodes, which means that it's absolutely balanced. It makes sure that the load is properly balanced inside the cluster. So if I have 5 nodes, it makes sure that the data is absolutely distributed across these 5 nodes in equal numbers. In the sense, like say if I have say 50 records and I have 10 nodes, so it basically makes sure that the distribution is almost close to 5 per node in the cluster. Random automatically makes sure that it is in a round robin fashion. It makes sure that it's actually rightly balanced inside the cluster. Whereas in the case of byte order partition, so how does the byte order partitioner is something which is special. which is meant to be mainly used when you absolutely know about your data and how you will actually organize it and what are the different types of queries that you would run. All the information, if you really know, then you can use byte order partitioning. We'll talk about the byte order partitioning in more detail. Okay. So how does the random partition process work? It basically gets a row key, so obtains a row key. It generates an MD5 value, MD5 hash of the row key, and the resulting hash value is restricted between 0 to 2 power 127 because the hash size, the total hash size which a Cassandra cluster uses to store the information is about 128-bit hash. So the total range is 0 to 2 power 127. So it will make sure that the hash that is generated is restricted in that range. Then it obtains a token associated for each node. So in case if I have 3 nodes, I basically create 3 different tokens, which means 0 to say 1/3 and 1/3 to 2/3 and 2/3 to 1. So you create basically 3 different partitions of the data and obtain the hash associated with your 1/3 value and then assign it to the node 1. Similarly for the 2/3 value into the node 2, and then the 1 basically will be assigned to the third node, assuming you have 3 nodes in the cluster. In this case, what it's basically showing is 0 to 2 power 42 is the first node, and 2 power 42 to 2 power 84 is the second node, and 2 power 84 to 2 power 127 is the third node. So it basically gives you a tool which you can use to calculate the tokens if you really know. So in case if I know when I'm deploying a cluster that the number of nodes are say 10, then Cassandra actually provides a tool as part of the distribution itself, where you can say, okay, my total number of nodes in my deployment actually is of data centers, 2 data centers or 1 data center, and what is the number of nodes in each data center. If you can say, it automatically gives you the token value calculated, and then you can just take the token value, put it in the configuration and start the node. Okay, so that's the way random partitioning process works. Okay, so random partition basically has advantages, naturally even distribution, because the data is rightly balanced inside the cluster. But the disadvantages wise, it's inefficient range queries, because say if I have data which is written into say 50 keys that you want to really write inside the cluster. So you take say first 50 keys and write one by one. Then the way it gets distributed is the moment you write your first key, it basically puts it into the first node. The second key goes to the second node. The third key goes to the third node, etc. So it tries to distribute it in an even manner. Because of which, if we have to run say a query from say 1 to 5, it basically has to fetch the data from 5 different nodes and not really from one single node. So that's the reason, efficiency wise, that if you are doing range queries, it's comparatively inefficient. But when it looks at the overall load inside the cluster, it's actually evenly distributed across all the nodes in the cluster. So that way, random partitioner is probably the default and the best one as far as the overall distribution is concerned. But if you're really doing a lot of range queries, or rather your application needs a lot of range queries, then probably random distribution is not the right way for you or application. Coming to byte order partitioning. The byte order partitioning, the concept is simple, where your tokens are actually calculated manually. In the sense, like, say I have to store data of say 0 to 1 million keys. So, and I have say 10 nodes. So you want to basically say, I will actually break it down into say 100,000. So each node will have about 100,000 keys, assuming that I have 10 nodes. Now the difference is, since I have made it in such a way that it's 0 to 100,000 is in node 1. So all data which gets written within that, or all updates associated with those keys, will go to node 1, and then the rest of the appropriately it's mapped inside the cluster. So because of which, in case if a situation comes in, like so you write a lot of data and a lot of operations are actually happening on a set of people, which is probably whose IDs are say from let's consider instead of 300,000 to 400,000 is what it happens are the set of people who are actually have the maximum number of updates. So in that time, what happens is that becomes a hotspot. A particular node is getting too many updates because you have done your byte order partitioning, where you have actually controlled, you have actually calculated the tokens manually, and you have done a manual assignment of the nodes. Say for example, the data here it says 1 to 999. So and then you've basically broken down your stuff, etc., into each of them having about 100 keys. Okay. Each of them have about 100 keys. Now what happens basically, so assume that you have a huge number of data that's coming. Say out of your 10 million rows you write into the Cassandra cluster. So assume that data is between 300 to 400 data range. And only 10% data is between 500 to 501 to 600. And then 10% is the rest of the data. The observation basically will be that all data will get written into node 4, which means almost like 8 million rows will go into node 4 because almost all the updates or anything that's happening is happening on the data which is from 301 to 400, which automatically creates a hotspot. That node becomes absolutely slow. Even though you have too much of capacity available in the entire cluster, you cannot really use because the node 4 is responsible for these keys, and because of which hotspot gets created. The cluster becomes very, very slow. The node becomes very slow. It takes more time to run the queries and respond back, even though you have a huge amount of capacity inside the cluster which is unused. So this is a problem with respect to byte order partitioning. And again, what happens when a node is added in case of the following: random partitioning or the byte order partitioning? Okay, so this is exactly what happens. So in the case of random partitioners, basically a new token range is quickly assigned because now it knows that there is a new node into the cluster, so that will actually automatically make 4 partitions, and quickly assigns the new partition, the 4th partition, to the new node. There's absolutely minimum amount of data moved from one of the nodes to the new node, which is now it is responsible for. So basically now, so the new partitioner is actually having some responsibility. So all the data associated with that responsibility will get transferred to it. But when it comes to the byte order partitioners, first thing is you have to add it manually, and you have to calculate the token size manually. So you have to calculate the actual token information and then place it in whichever place that you want, whether you want to place it between 3 and 4 or 4 and 5, you have to define, calculate the range and manually add it to the cluster. This is exactly what happens in the case of byte order partitioning. So how does the replication work on pretty similar lines? So you opt in the hash, and the hash is returned to a particular node. First choose the node, in this case the green node. So the green node is your responsible node, and then it will use depending upon your replication factor, if it being 2 or 3, and then appropriately using the strategy. So the strategy is simple, then it will find the replica as a immediate text node in the cluster, traversing in the clockwise direction. So in this case the red node, and then the red node actually will be the place where you will store the replica. Okay. Pretty much again the similar stuff which we talked about. Simple strategy naturally is the clockwise nodes. There is absolutely no consideration for rack and data center location in the case of simple strategy, but in the case of network topology strategy, it automatically takes care of that one. One second. Okay, so the simple strategy, network topology strategy, is for the sake of because we're talking about administration where all these things actually be part of it. So that's the reason it's been just mentioning here. So assignment is absolutely based on the partition strategy. So it will always try to find a different rack for placing the replicas. So in case if no racks are available, it automatically falls back to the simple strategy and uses the clockwise mechanism. That's the reason why now the new mechanisms is saying that the default one is network topology strategy, because it falls back to simple network strategy in case if you don't have multiple racks or multiple data center deployments. Whereas in the earlier case, it used to simple strategy was the default one. Now it's network topology strategy is the default one. So in case if it doesn't find any racks or new multiple data centers, it automatically falls back to the clockwise mechanism of simple strategy, and as a result it becomes it is the default strategy that is used inside the Cassandra cluster deployments. Okay, coming to snitches. So what is a snitch? Snitch basically is it determines relative host proximity. As I said, it's something which helps in the better routing inside the between the nodes in the cluster. So it gathers information about your network topology so that it can route the requests in a more efficient manner between the nodes. That's the main purpose of the snitch. So there are different types of snitches that are there. And the default one basically is a simple snitch, which is used in the case of general single data center deployments. And simple snitch actually follows a pretty similar kind of a model of it knows that it's actually you're following simple strategy, so it knows how to actually locate the nodes, because you're talking about clockwise direction, all sitting in the same data center within the same rack most often than not. So its simple snitch will do the job for you. But when you have, say, multi-data centers and multiple racks and etc., there are different types of snitches called rack and data center aware snitch, etc., that will be used. And all snitches are absolutely compatible with any replication strategy that you use. So it hardly matters which replica placement strategy that you use. They're all compatible with everything. What are the different types of snitches? So if you look at it, these are the various types of snitches that are available. One is a simple snitch, which is the default one, and always used in the it comfortably uses the same concept of walking clockwise through the nodes for routing information. But when it comes to rack inferring switches, it automatically tries to place the copies on different racks in your data center. Very important, because it tries to make sure that the rack inferring switch will make sure that the copies are placed in different racks so that you have rack failure can be avoided. So in case even in case of a rack failure, you still don't lose data, and the copies are still available for you to serve the request inside the cluster. So rack inferring snitch actually uses the location of the racks and make sure that the copies are placed in different racks. It uses the IP to infer the network topology, and the second unit of the IP address is used to identify the data center. We'll look at this actually. There's actually a file called Cassandra topology.properties, which is what we call it as a property file snitch. Allows you more control when using a rack aware strategy. So it's something called Cassandra topology.properties, which gives you information about the location of your replicas, or rather the nodes in the cluster, and and which data center they actually belong to. So all this information is actually provided inside a file called Cassandra topology.properties. And there is another level of other snitch called EC2 snitch, which is very specific to Amazon clouds, Amazon Elastic clouds. The advantage basically is in the case of Amazon, the location of your VM or whatever is available to you, it keeps changing because you don't really know the physical part of it. That's the reason EC2 snitch actually uses Amazon's AWS based API to determine the actual location of your node in the cluster, and then uses that APIs to actually route it efficiently inside the Amazon cluster. That's the reason EC2 snitch is used when you are setting up your cluster inside Amazon EC2. Actually, we use it in our deployment. Actually runs completely my old company. The entire deployment used to run inside Amazon. We have about some 2000 nodes or something that we run inside in Amazon cluster, and all of them actually use EC2 snitch because which really helps in locating as well as efficient routing inside the EC2 cloud. Okay, cool. So Cassandra topological properties look something like this, where it says the IP address of the node, which data center it belongs to, and which rack it belongs to. So this is the format in which it is written inside Cassandra topological properties. The first one is IP address, second one is the data center, third one is the rack details. Every node in the cluster should have this file, and this file should be exactly the same in all nodes in the cluster. Okay. The first one is IP address, second one is the DC1 or DC2 is the data center, and the third one is the rack 1 or rack 2 details. So coming to monitoring Cassandra. So as we said, Cassandra is a Java application, right? It's actually something which runs inside a JVM. So Cassandra provides you Java management extensions, which sort of helps you in monitoring the Cassandra system pretty well. So it provides you, and I'm sure anybody who's worked with Java would know what JMX means. Java management extensions actually is a mechanism. It's basically a sort of a stubs or something like hooks which are provided inside your application, which you can use from the external world. As an outsider, I can connect to these hooks and obtain useful information about the application runtime. So that's the mechanism which JMX provides out of the box. It's very commonly used for a variety of Java application controls, application control operations in any of the Java applications. So for example, low available memory detection, thread deadlock detections, etc. So you want to understand about the class loader tracings, log level control, and even provides you some management capabilities where you could force some operations on your Java application using your hooks. So the hooks are actually provided in such a way that you can run an operation on your application directly from there. You can do that. I'll show you how do you actually work with that when it comes to Cassandra. Simplest way is to, another option is say there are a lot of tools available in the commercial world. So one thing which is available in DataStax is it provides you something called an ops center. So you use the ops center and you can actually monitor the Cassandra cluster comfortably from there. You can actually even do a lot of management activities where you could add, remove nodes from the cluster and etc. So in addition to that, there are some open source tools like MX4J and etc. which could be used to monitor or your Cassandra clusters. I'll show you how do you actually work with something called JConsole, which when you're coming to management extensions. So when it comes to monitoring, what are the key attributes that you need to track per column family? So there's something called read count, read latency, write count, write latency, and pending tasks. So when you see that the queue of pending tasks is increasing, which automatically means that the node is not able to pick up your tasks and it's able to process it, which automatically says that your node is going to get slower and slower and slower. So your read and write latency will tell you exactly what is the time it's taking to process a read request or a write request. Okay, so these are the set of attributes that you really want to monitor on a per column family basis. Now maintenance. So what is maintenance? Maintenance is basically when you want to actually say obtain information about the different statistics which are there inside the node. You want to obtain the ring information of how the ring is performing, what are the total number of loads which are alive. You want to bring down or bring up a node. You want to create snapshots. You want to do some load balancing, and some basic maintenance as to like you want to say just get your thread pool statistics. You want to get your information on what's happening inside the node. So in all those cases, you want to have some sort of a tool. So Cassandra provides you a tool called node tool. So the node tool actually helps you to achieve all these things. It looks at your cluster, understands and modifies its activity. It gets limited statistics about the clusters. You can see the range each node maintains. You can do moving data from one node to another. You can decommission a node. You can repair a node that's having trouble. So node tool is something which is available by default in the open source distribution itself. Okay, so just look at some of the things now. Okay, so there is something called info. So if you say node tool, give the IP address to which you're particularly connecting, and then say info, it gives you information about your ring. So some of these things got changed in the new versions where you call it a status and etc. But we'll run some of it and then we'll see what it provides, what are the kind of information that it provides and etc. Okay. So you pass the address of the node to which you want to connect to and then obtain the information about the ring. The info is the command. Similarly, you have commands for different things. Like if you say ring, it gives you the ring information where you're talking about basically the different partitions which are there and what is the status of each of those partition or the nodes itself. Say in the case of right now, it's like if you say ring, it basically gives you, here it's showing up with a physical address, physical IP address, which is actually is the partition that a physical node shares, and it's saying what is the status of each of those partition, whether it's up or down. In the case of virtual nodes, it actually shows many partitions like this inside the cluster. We'll see some of it anyways. Yes, we'll see in practicals. Then it provides you two different types of stats, what we call it as CF stats and TP stats. CF stats basically means column family statistics, and TP stats is basically the thread pool statistics. So you can actually see all this information using node tool and understand how the system is performing, what is the information that you have available. So how is it performing today, and what are the different types of information that it provides as part of these statistics. We can look at all these things. Similarly, it can give you, when you say TP stats, it gives you information something like this. So we said this is because of SCADA, right? So there are many thread pools which are there inside the Cassandra cluster. So one is like file utils, messaging service pool, stream stage, response stage. So there are many different types of thread pools that are there, and it shows what is the number of active threads inside the pool, what is the number of pending requests, and how many have been already completed so far by the thread pool. So it provides you information on these lines when you run the thread pool statistics. So on the basic maintenance stuff, you could do repair, flush, cleanup, etc. So there are another set of commands which are provided by the node tool. Repair basically is when you want to repair a particular node because it has some issue or it's not really having a proper synced up inside the cluster, and you want to basically repair and make sure that it is back to normal and everything is working fine with it. So you can use repair, which actually causes Cassandra to execute a major compaction, make sure that everything is, all the unwanted stuff is thrown out, and then it makes sure that it's actually back to normal and working together as a normal node, any other normal node in the cluster. So you provide a key space as an argument where the compaction is required, and then you run it on a specific host, connecting to a specific host. Okay, so similarly you have flush. Flush actually means that you actually flush your mem tables to the disk. So this is another very common process that's used by the administrators, is whenever you want to really do some maintenance activity in the cluster, you don't want any in-flight data. So basically something which is sitting in the memory. So you don't want any in-flight data. So you could actually do is you make sure that you run flush on the system so that everything is flushed to the disk from memory. And then afterwards you do all your maintenance activities, removing, adding a node, and etc. All the stuff you do it as post that one only. Similarly, there's something called cleanup that you can do as part of the maintenance activities. Generally used when you want to change the replication factor or the replication strategy. So the purpose is, say today I have a replication factor of say 3, but over a period I felt that my replication factor is from 3 I have to change it to 2. Then you have to run a cleanup. But ideally, yeah, you would rather not want to do it, but if it's an absolute need, then you can do it using cleanup. You don't change the replication factor later, because it's end of the day, it's simple, right? So if I have say 3 replicas which I have been maintaining all along, and then suddenly if I change it to 2, which means that my third replica has to be discarded across the entire cluster. So that's the reason it's called a cleanup task, where it ends up cleaning up the third replica and making sure there are only 2 copies of all the data that's stored inside the cluster. This might take a good amount of time to make sure that some of these things are done, but it surely provides you an option to do it. That's what it means here. Okay. So as it flush and cleanup are another set of commands that are used for mainly. One is flush for flushing your mem tables to the SS table, so the disk-based representation. And cleanup is used when you want to change your replication factor or replication strategy. So just so that you sort of clean it up and make sure that it's actually taken care across the cluster in all the nodes. Okay. Then snapshots, another very important data backup mechanism. So in case if you want to say what's the purpose? Basically, you make a copy of all of the key spaces in node and save it to some different place, so that you have a separate data place file which you can use in case if the node fails. Say for example, if the node goes down, and then you can actually restore it to one of your previous snapshots, and then allow it to sync up and across the replicas and bring it back into the absolute sync across the cluster. 1 hour previous snapshot, and then that 1 hour previous snapshot basically will be out of sync with a set of data, right? So that data, it will get synced up in a shorter form. So assume that you don't have a snapshot. So if you don't have a snapshot, basically it has to sync up all of the entire data, right? It has to sync up the entire data from the other replicas in the cluster. So that takes longer. So because of which snapshots are very, very useful. And the way you take the snapshots is using just the snapshot as a keyword, or you want, for the entire node, or you can take it to a single key space using the key space name followed by the snapshot keyword on the node tool. And when you want to restore, you basically shut down the node, you remove the old SS table and commit log, copy the data from the snapshot directory to the regular directory, and then restart the node. And then it automatically restores it to that particular snapshot, and then it will start running continuously from there. So snapshots, as I said, is very, very important, and it should be used in Okay, so then coming to decommissioning a node. When you want to really decommission a node, these are the steps that you need to follow. So the mechanism that actually it follows is, where you could actually do using node tool, and say you can say decommission a particular node as the command. Then what happens is, it happens in this sequence. The operations that happen inside the node are in the sequence. First, it shuts down the gossiper, because so it doesn't receive any of the data from the other nodes. Then it brings down the messenger. The messaging service is shut down, and then it brings down the data manager, so that all your thread pools and everything that are there for the different stages, these are all brought down. Then it marks the status of the node as decommissioned, and then So as far as the rest of the cluster is concerned, this particular node does not exist anymore. So the node is gone, and then you have only two nodes in the cluster. In this case, the node ABC. So the B is gone, and A and C are the only two nodes where the partitions are actually readjusted so that the entire data is occupied in these two nodes instead of the third node, which was supposed to be there. What's the process of making a database snapshot across different nodes? So there is no specialized process as such. So you have to take your snapshots on a per node basis. It's not really across different nodes. There is no way to do it across different nodes. The node tool is basically for your particular node. So you have to take snapshots of each node separately. There is no simple way of doing it across all the nodes in the cluster. So it could be something like, okay, you probably could write a program or some sort of a process which actually picks up all the nodes and runs on each of them as a remote process or something, and takes a snapshot of everything. That can be done, but it's basically an automation mechanism that you would actually create it, but there is no direct way of doing that in the cluster. So the node tool actually works on a per node basis. So you have to do it on every node. Performance tuning, let's talk about it in detail. Okay, so first let's go back to running some practicals, and then we will come back to performance tuning. Okay, so we looked at G-console, and then let's run some node tool. So it's in the bin folder. Okay. I'm just saying localhost because this is my running on the local system. So if I just say status, it gives me the status of the cluster. Here what is it saying is, it's basically saying I have 3 nodes in my cluster, and the partition ownership of each of them, what is the total load, what is the number of tokens. So the tokens, if you see it, basically 256 is what it says, which means that it's actually talking about virtual nodes. We'll talk about what virtual nodes are. Give me a second, okay? So then it's saying what are the racks that it uses, because it's simple deployment, which is only single. There is no specialized rack, so its default is rack 1. And when you say UN means it's up and normal. So it's the status which is showing here. So if you see, it means it's up and it is normal. So this is basically the way to monitor your status of the nodes in the cluster. So what I'll do basically is, now I'll bring down one of them. Okay, I'll bring down one of the nodes just to see how it behaves. Okay, so if I run this again, so it says down. It says down and normal. So it is up and normal or down and normal. So if in case if it's in a bad state, like it's actually leaving the cluster, like if you're decommissioning or you're basically adding a new cluster, then you will have other states like leaving, joining. And then if you want to move, when you're moving data from one to another one, from one node to another node, it will give you the other statuses called moving, joining, and leaving. They're pretty much something which we will be seeing in the practical scenarios. Right now, I just brought down the instance, so it says normal. So if I restart the node, it will basically say it's up and normal again. So right now it's down still because it's not started. So it's still down, it's not started. Now it's up and normal. Okay, all of you can see that, right? Okay, so similarly, instead of status, if you say ring, right? So ring shows so many things. Did you see that? It basically shows huge number of things here. But if you look at it, what is it showing end of the day? If you see exactly what it is showing, 1 second. Okay. So it says if you look at it, it shows the same IP address 127.0.0.3, then 127.0.0.1, and then 127.0.0.2, etc., etc. So what's it actually end of the day showing is it's basically showing a virtual partitioner. So each node has about 256 virtual nodes, and it's showing all the virtual nodes in the ring. And how does it work? Okay, if you just go back a little bit just to understand, I'll show you what happens. Okay, so this is the way it works basically. Okay. Okay, 1 second. I think I have a presentation. 1 second. Where am I? Okay, so if you look at it here, the concept is basically as long as right now when we create a ring, we create a ring with the node as a set of partitioners, right? So I have say A, B, C, D, E. I have like say A, whatever, doesn't matter. Node 1, node 2, node 3, node 4, node 5, and node 6. That's the default mechanism which is at the top. Now the actual virtual nodes, what happens is each node is by default broken down into 256 virtual nodes. That's a default number, but you can reduce, increase, whatever you want, whatever is suitable for your need, you can do it. It all depends on how much amount of partitions that you really want to do. Okay, so what happens is each node is broken down to smaller pieces. So what is the cluster? The cluster looks like something which is similar on shown at the below the line. So the cluster basically has now small partitions, and it's formed with the small partitions. But right now there is still no advantage, because each node, the partitions are still together, right? So because of which you are still representing the set of partitions as by using the physical node itself. So what happens next is it actually does a shuffle at the partition level. So when it does a shuffle at the partition level, so what is it doing? It's basically shuffling at the partition level now. Now each node is basically broken down, and then it is actually shuffling the virtual partitions. In a way, there is the dependency on the physical node for a specific partition is gone away now, because all your data is actually dealt with at a much smaller granular level, which is basically the 1/256 of the actual partition in a way, because you are making each partition into 256 small pieces. Now this is the advantage basically is when you make it out into this set of virtual partitions or virtual nodes, whenever the node goes down, the amount of time it actually takes to bring it back is much faster, because you're dealing with smaller partitions, and smaller partitions are not really all of them are not really the master copies here in a way, right? So they can actually do shuffling back and forth very easily, and somebody who's not a master copy, who's just basically a replica of another one, they could actually get synced up with the appropriate replica in the other node, and etc. So it's like you're dealing with data at a much smaller chunk, which means all your copy, recovery, everything that you're really working out or rather manipulating does not have any physical dependency anymore, and it's easy to work with that because the chunk size is reduced quite a bit. So that's the advantage of virtual nodes, and by default it's virtual nodes right now. So each node basically it shows us as 256 as the default virtual nodes. But if you really don't want to use virtual nodes and you want to go back to the physical node concept, you can always go and change in the configuration from num tokens. The configuration parameter is called num tokens, where it actually says 256 as a default value. So instead of that, you take it off and put it as initial tokens, and it will go back to the node wise clustering mechanism, which was the older mechanisms. But since virtual nodes is a much better feature, and it actually helps you to shuffle the data much better inside the cluster, and it helps you to deal with data in smaller sizes, the smaller chunks, which surely takes away the physical dependency, as well as it really helps in recovering or any of the other operations, because now you are operating on smaller chunks than actually the bigger chunk, which is the node level chunks. Make sense? This is the virtual nodes concepts. So here what it's showing is basically the virtual nodes. Okay, so now let's run the ring. We did status. We will do what say CF stats. So column family statistics. It shows all the column families in the statistics. So these are the things that it shows. So for example, I have a key space called roads. It shows what is its read count, what is its read latency, what is its write count, write latency, and the pending tasks. So it shows information about all these things on a per key space basis. What is the compacted partition, maximum bytes, minimum bytes, local write latency, local read latency, mem table data size. So yeah, it basically throws information about all column family statistics in the entire system on a per key space basis. So if you look at CQL hotels, it's showing the SS table compression ratios. See here, if you have the space used, SS table compression ratios, number of keys which are there. This is just basically a example that I have used for running some CQL query. So if you look at it, what is the Bloom filter space used, compacted partition, maximum, minimum bytes, mean bytes, etc. So all this information is something which is provided on a per key space basis. Will you be able to access each of the virtual nodes directly? What do you mean directly? What is it you want to do actually? That's the question, Sneha. So what is the purpose? What do you mean by able to access each of the virtual nodes directly? See, they are not really a physical entity. They are not tied to a physical entity in a way, but you surely have the token information, right? When we ran the command, it showed the token information, right? So this is the partition token hash, right? So this shows what is the responsibility of, or rather, where that virtual node starts and where it ends on a specific node. But when you say access directly, what is that you want to do? What is the concept? What is that you're looking at actually? So you're saying, will I actually entitate? Yeah, basically yes, right. It would be maintenance would be easier because now you're dealing it at you don't have all the chunks of the same node in the same host, right? Because the smaller chunks are shuffled across the cluster. So now the cluster is basically of, say, if I have 4 nodes, you're talking about almost like 1024 small partitions, and you're not really talking about four big partitions. So naturally smaller partitions are easy to manage because when you're copying it across the nodes, or when you're actually repairing all your stuff that you're doing it at much smaller sizes. That's the reason I said the maintenance would be much easier. Make sense? So as I said, CF stats, we saw what it shows. Then TP stats, this talks about all the thread pools inside the system. So TP stats shows exactly similar to what I've shown you. So it's on a pool name, active, pending, completed, blocked, all-time blocked. So if you see any of these stuff actually blocked and all-time blocked, you clearly know that something is stuck in the system and you need to clear it out. So the thread pool statistics shows something like this, and then it shows about all the message types also, like what is the number of request response messages which have gone into the system, what is the read repair range slices requests that have gone into the system, the mutations, basically the number of queries that you have combined together, and if there is anything which is dropped out of them, something which is already made but it's dropped. So it shows all these information as part of the TP stats. And all the different thread pools, hinted handoff, everything is a stage, as I said, right? Everything is end entropy stage, migration stage. So each of them is a stage, and each of them has its own thread pool, and those thread pool is actually showing the information. Say gossip actually has a maximum here because gossip naturally does so many things because it just talks to the nodes on a regular basis. Even though I have not done a lot of work on this cluster, the gossip is still a big number because it's whenever you bring up the cluster, it actually uses, it runs a lot of gossip messages back and forth. which are again handled by the gossip thread pool. Okay, so that is TP stats. Okay, let's do one thing. I'll just run this to see what are the various other things that are available. Okay, so you look at it just for the sake of understanding. And actually, they've improved the node tool quite a bit from what it was earlier, because now it provides you too many options which you can do. So all the available commands, so something called CF histogram, CF stats, cleanup. We talked about cleanup. Compact. You want to run compaction directly on a specific key space and column families. You can run it. Force if you want to force it. Okay. Compaction stats. Yeah, this is another interesting stuff that you need to look at. Then you sense it describe cluster. That's another thing which actually talks about. It prints the names, niches, part niches. Let's look at some of those things. Okay. And then get SS tables, stream throughput, gossip info. If you look at it, okay, let me just run some of it. Okay, gossip info. So this talks about the gossip info with respect to this particular node with the other nodes. So if you see this is basically what it maintains on a per node basis. What is the status of each node? Is it normal or not normal? Which data center, which rack, what is the severity, host ID, RPC address, release version of Cassandra that it's running. So all information that it actually maintains inside its gossip information on a per node basis. Similarly, you said compaction stats, right? Okay. So compaction stats shows about, it shows basically pending tasks and active compaction remaining time. So in case if you see any of these stuff, it means that your compaction is running right now and there is something which is pending for you to run the, basically it's about to run the compaction, or it's running the compaction. And most often than not, this is one case where you can actually check if the particular node is, when it's a particular node is very slow and it's performing really at a much lower level than what is its actual capacity. So some of these things could be give you information about what is actually happening at the time. So if in case if it shows pending tasks and some active compaction remaining time as some values, then it automatically means that it's actually running compaction at this time, because of which you might see some performance issues in the system. Okay, so then what else we said? Describe cluster. Let's look at describe cluster. So describe cluster says the name of the cluster is test cluster. It uses dynamic endpoint snitch. Then partition wise it's MOMO3 and schema versions. These are the 3 nodes in the cluster, and that's the version of the schema that all of them are running. Okay, and then what else? What are the other interesting stuff that we can look at? The ring we looked at. Repair and all is not going to work right now because you cannot do any of the stuff here, because I have to bring it down and I have to create some bad situation, and then only you can use repair and etc., which is not a straightforward thing. Then you have snapshots. Okay, snapshot. If I just do snapshot, it goes and creates snapshots for all key spaces. So it has created a snapshot for all key spaces. So if you go back var lib Cassandra data, so which one has some data? I don't know. Okay, let me just look totals. None of these have some data, is it? Okay, snapshots. It writes into the snapshots folders for each of them. See, this is what it is, the created one, right? Okay, see this here in this one. The snapshot directory that it's created is basically the it actually names it in line with that one. Okay, so you look at for this particular number, go to this particular directory, and this has a snapshot which is the latest snapshot that you have created. So it has created a snapshot for each of the databases. So all these databases are actually the ones which are for it, it's created a snapshot and put them into this particular folder. Okay. So similarly, it would have done for everything because I didn't give any specialized. So Murmur partitioner is the default random partitioner, which the Cassandra uses. The latest version of Cassandra 2.0 onwards, they use what we call it as Murmur partitioner, which is nothing but a random partitioner. But Murmur is basically an algorithm which is used for event distribution. It works better than the older random partitioner which Cassandra used to use. And right now, the Murmur partitioner is the default randomized partitioner that's used inside Cassandra. Okay. So yeah, this is the snapshot. Okay, so go back to Cassandra. Okay, $/node tool. Okay, snapshots we did, and what else do we have? Anything interesting that we can look at? Okay, so this is another interesting one, but we don't do it right now. Something called scrub, which actually rebuilds SS tables for one or more column families. So you can use it if required. When you see that something is not really in place, you could use it for scrubbing. Refresh, remove node is one thing which you can use to current node removal. So it basically forces the completion of everything and then remove the provided ID. So as I said, the existing node tool, the new one, which is actually which comes with 2.4 and onwards, provides you a lot of options which the earlier version never used to provide. So describe ring shows a token ranges info of a given key space, etc., etc. And there is another interesting stuff. So you see there's something called enable auto compaction, etc. for specific key space column families. You could do this also here. Enable backup, enable gossip, or disable gossip. You can do all this stuff if you want to really. Basically, it provides you a very minute level control that you can do on a per node basis. SS tables, compaction throughput, and then etc. all the stuff. Set, get, threshold, cache key store. These are probably the ones which are interesting, but you can try each of these things offline, and then you can look at some of the information there. That is one which is related to that, and then describe what we said is ring. Hey, what happened? We did describe cluster and describe ring also, right? This works. So what is describe ring? Okay, it didn't work. Am I typing that command right? It was describe ring and key space. Okay. Describe ring and say key space hotels. Okay, so this gives you an absolute token range of the key space per node. So on 127.0.0.1, what is the token available? Start token, end token, the actual endpoint which is happening, which has information about this key space, etc. in the entire cluster, how this particular key space is distributed inside the cluster. This is like the virtual nodes which you talked about, right? So you have a start token and token, very similar to this. You will have it per virtual node. There's something called a start and there's something called end, which is the responsibility of that virtual node. Okay. So yes, yeah, and decommissioning and all I'm not going to do right now, because those are more of I want to pull out the node and etc. from the cluster. Okay, we have something called info, right? Or info gives you this kind of information. So it gives you the node information, basically token, the ID, is the gossip active, thrift is active or not. Then you transport layer, the generation number, which is basically an ID for this particular node, data center 1, rack 1, key cache, row cache, etc., etc. Information about this particular node, and it's an ID. This is the ID, hash ID of the particular node. Okay. So that is the node tool part of it. What else? What else do we have? I think the first, last, and final thing is the performance tuning. So we'll probably do this and close for today. So on the performance tuning wise, right? If you look at it, what are the major important things that can affect the performance? So one, naturally, if you have a bigger memory, which means your bigger mem tables and bigger caching, row caches and key caches will be big, which means your overall read performance increases quite a bit. So a bigger RAM automatically gives you a better performance. So that's one part of it. And then when it comes to writes, it's always recommended that you use a separate device. So basically, if you have multiple disks that you are using in the system, create commit logs on one of the disks and the other writes on the other disks. So all your SS tables and etc. will be in a different disk. So that gives you basically a better IO throughput on a regular basis, because there's a lot of writes which are happening back on each node. So automatically that works better for you. If you have two different disks that you use for your commit logs and your general writes, which is your SS tables and MM tables and etc. So sorry, your MM tables to SS tables and etc. So you basically try and create two different disks, one for commit logs and one for this one. And then in addition to it, the general performance, right? When it comes to Java, it's a Java application. So you have other things, basically your concurrent threads which you are running in the system. So we saw that when we ran the JConsole, it showed that the concurrent number of threads that are available, or the total size of the read-write threads, is about 32, which is most often than not more than enough for most of the general cases. But if you want to really increase it and assume that you have more codes, then you can raise that to 64 and all, which might give you a better performance compared to what it is. But 32 is more or less enough because of the SATA system that it works. 32 is more or less enough for very high loads in general. But if you have more cores and more CPU power at your disposal, you can always increase that to 64 and all. Okay. In addition to that, the general GVM tuning and everything will work. So basically, you want to basically change your garbage collection algorithms. You want to increase your heap space. You want to increase your some of those parameters could be tuned very similar to any other Java application, because it's a JVM based Java application. So you can use all your general Java performance tuning also as part of for Cassandra performance tuning itself. Okay, caching, memory, separate device for commit logs, etc. And then the general performance tuning of Java. So that's, I think, what it is with respect to performance tuning Cassandra. Are there any log files? Yes, there are log files. What do you mean log files? Are you saying with respect to the general running of Cassandra? That's already here, right? So when I actually run it, I'm actually running it in the foreground, which means that all my logs are actually being shown in the console. So when I run it here, they're all sitting here, right? This is the logs. Anyways, these are the logs here. But if you don't want to run it, it will go right to another log file. That's not a problem. But console helps me a lot better, so I use console most often than not anything else. Okay. This is commit logs and data and save caches. There is no other special law which it creates to the extent that I know. So there is something called var log Cassandra. So this is a system log here. This is all the information associated with the system. This is another log file which is there, which will show information about the particular thing that you have. Everything that's actually running on the system, it gets logged into the system.log. So basically, how do you actually give information or rather permission to a particular user inside the cluster? So I can actually say somebody has admin permission, somebody has just a read-write permission, I can create multiple levels of permission per key space if required, because the authenticators and the system which are available, they can be modified appropriately. So I'll just show it to you for now, but we'll probably run it in the next class. Okay, so if you look at it, okay, so we are looking for a conf, right? Okay, so we are Cassandra.YAML. So if you look at authenticators here, so there is something called the default authentication, which is basically allow all authentication. Allow all authenticator is the default one which will be used here. Allow all authorizer and allow all authenticator are the default ones which are used. But you can change them to password authenticator and Cassandra authorizers, which are indirectly, which will give you control on different types of permissions that you want to create on a per key spaces. And you can actually create key space wise permissions, just very similar to the grant that you do in your RDBMS world, right? Where you want to say grant write on something, grant read on something. All those stuff can be done on pretty similar lines using on authenticators and authorizers. So change the authenticator. I mean, I could do it, but it's I have to shut down, restart, and etc. So I'll show it to you in the next class. So password authenticator I can change, and then once I shut down and restart, automatically the new node will work on the password authentication mechanism, which means that if I don't give a password, it will not work. It will not allow me to log in. So all those things will actually can be done at the authorization and authentication levels. Okay, thank you. Bye-bye.